We tap glass screens, and data flies across the globe. We trust small boxes to keep our hearts beating. It feels like magic. But underneath that illusion, every server farm and medical device relies on something entirely physical: the absolute microscopic control of raw electricity. Without that exact control, the illusion breaks down fast. Let the voltage spike by a fraction, and physical components melt. Data corrupts instantly. Human hearts skip a beat or stop altogether. Go back to the 1950s, right before the digital revolution kicked into gear. Engineers were hitting a massive wall. Early technology was simply too fragile for the complex operations people were dreaming up. They called it the stability crisis. To manage electrical currents back then, you needed massive, clunky control panels covered in analog dials. These machines were highly prone to catastrophic failure. The flow of electricity couldn't be managed with any real precision, meaning whole systems could overload at a moment's notice. The digital age was stuck in traffic. Progress was completely paralyzed until someone could figure out how to build reliable, precise breaks for these electrical currents. That bottleneck was broken by an American inventor from the diaspora named Otis Boykins. Boykins engineered the physical backbone of almost every device we use today. Yet, if you look through standard history books or lists of tech pioneers, his name is almost entirely absent. His historical footprint is profoundly obscure. Boykins, the man who tamed electricity for the modern world, is as invisible to the public as the microscopic component he perfected. Boykins didn't approach engineering looking for flashy features. His philosophy was rooted in relentless, practical focus. He cared about extreme precision and fail-proof reliability. He developed this mindset while navigating the racially segregated landscape of mid-20th century America. As a Black inventor, Boykins faced systemic barriers and harsh professional realities that denied him funding, credit, and basic access to the broader engineering community. Despite these immense external pressures, he didn't pivot or give up. He kept his focus locked entirely on solving the biggest technological hurdle of his era: electrical resistance. His lived experience demanded a profound level of resilience and stability merely to survive in his field. Those were the exact traits he would literally engineer into his greatest invention. Think of electricity in a circuit like high-pressure water rushing through a pipe. Without a reliable break, the energy floods and destroys the system. Boykins built an exact, unyielding break. His component drops into the line, instantly calming the flow into a steady stream. This is what that component looks like in reality. Boykins perfected this simple, compact, wire-wound design. Because they were small and straightforward to produce, they could be rapidly mass-manufactured for factories around the world. Standard resistors of the time fluctuated wildly when they got hot or were bumped. Boykins' precision resistor could withstand extreme temperature changes and heavy physical shock without losing a single fraction of its exact electrical resistance value. With this indestructible stability finally secured, engineers were free to shrink their designs. They could miniaturize technology safely without the constant fear of a sudden, explosive component failure. That exact stability immediately saved lives. Boykins resistors provided the specific, long-term electrical reliability that allowed the first medical pacemakers to function safely inside a human chest. A pacemaker is a device that cannot fail. It has to deliver exact electrical pulses to a human heart, day in and day out, for years, without a single microscopic error. Boykins' resistor provided that literal life-or-death guarantee. Zooming out from the human body, this same stability allowed for the birth of the modern computing era. Early commercial computers were physically massive, filled with thousands of intricate wires and vulnerable components. To execute complex logic operations, these machines required thousands of perfectly stable parts acting in unison. A single burned-out wire could ruin hours of calculations. Boykins' invention provided the stability required to scale this processing power safely. Whether it was regulating the pulse of a failing heart or processing millions of corporate data points, the foundational requirement for success was the precise control that Boykins built. Over the next few decades, those massive, room-sized machines steadily shrunk. They moved onto our desks, into our homes, and eventually into our pockets. So why is Otis Boykins still profoundly obscure, despite architecting the physical foundation of our entire technological reality? The answer is poetic. Boykins' historical legacy operates exactly like the physical resistor he invented. Otis Boykin remains hidden deep inside the complex machine of history, rarely seen by the everyday user, but absolutely essential for the modern world to function.